Now we'll look at the actual mechanisms of bioeffects, so the different ways in which ultrasound can affect tissues. Potentially harmful bioeffects are categorized into two major categories. The first of these is thermal, which of course refers to heating of the tissue. This is sufficiently well understood and sufficiently important that it is a category of its own. And then everything else is gathered under a second heading and referred to as mechanical bioeffects. The most important mechanical bioeffect, which I'll describe shortly, is cavitation. So we'll start by looking at the heating of tissue. You'll remember that ultrasound's absorbed by the tissues as it passes through those tissues, and this causes heating. What's going to affect the rate at which the tissue heats and the amount that it heats? Well, the ultrasound frequency is important. You may remember that attenuation is exponentially related to frequency. As the frequency increases, the attenuation increases dramatically, so heating is going to be much more pronounced at high frequencies than at low frequencies. Of course, the ultrasound power, the actual exposure levels, are going to have a very direct effect on the heating. The absorption properties of the tissue, whether you have normal tissue or whether you have tissue with pathology that makes it unusually absorbent, is obviously going to affect the heating rate as well. And then finally, something that may be less obvious is the question of whether or not the beam is scanned or stationary. Now, the beam scans in order to produce grayscale images and color Doppler, but it is stationary for pulse Doppler, CW Doppler, and M mode. In all those modes where the beam is stationary, the transmitted energy is concentrated in a very small amount of tissue. It's not being distributed around by the scanning of the beam. So the heating effect in that local area is going to be greater when the beam is stationary. So far, we've talked about the heating of the tissues, but there are also mechanisms that carry that heat away from the tissues. If you think about a saucepan on the stove, and that's being heated by a burner underneath it, then heat is being applied just to the bottom of the saucepan. But the entire saucepan becomes hot because the heat is conducted. Also, the liquid inside becomes hot because it's in contact with the saucepan, and therefore the heat is conducted into the liquid as well. Then the heated liquid circulates because the hotter liquid rises to the surface and you get a circulation of the liquid, and we refer to that as convection. In the body, there are equivalent processes. Heat is carried away from the area where the heat is being applied by conduction. So the ultrasound is heating a certain volume of tissue. That heat then spreads out into the surrounding tissues and the temperature reduces. So the heat is being distributed over a wider volume of tissues. In addition, when blood flows through the heated tissues, it takes some of the heat and removes it and carries it off to other parts of the body where it's then distributed. So, in fact, blood flow is quite an effective way of cooling the tissues. And if you think about it, this is very similar to the cooling system in a car. So we have two processes. The tissue is being heated on the one hand by the ultrasound, and the tissue is being cooled by conduction and convection. Those two will reach a point where they're in equilibrium, and then the tissues won't heat any further. So the heating process looks rather like this. We have an initial rapid rise, and then the temperature plateaus. Heat is being applied to the tissue, and heat is being removed from the tissue at the same rate. We therefore have a stable temperature at that time. So if you apply ultrasound for a long period of time, the temperature won't keep on increasing. It reaches this plateau value and stays there. The time scale of this graph is typically around a minute or a little less than a minute. So that's the sort of rate at which the heating occurs. The machine models the heating process and provides us with a parameter that's displayed on the screen known as the thermal index. The definition of the thermal index is shown here. It's equal to W divided by W degree, where W is the output power the machine is actually creating, and the machine knows that. It has all the parameters available to it to calculate that value. W degree is the value that it calculates using a model of the heating process, and it's the value that would give a maximum temperature rise of 1 degree Celsius. So you can see if the thermal index is 1, then we should expect that the maximum temperature rise in the tissues will be around 1 degree Celsius. If the TI is 1.5, then we'd expect the maximum temperature rise might be around 1.5 degrees. There are in fact 3 different models that the machine uses depending on the clinical situation. It will display TIS if there is just soft tissue around the focal region of the beam where the intensity is greatest. It will display a different value, TIB, if there is a soft tissue bone interface in the region around focus. And the reason for this is that those interfaces between soft tissue and bone produce significantly greater heating. Obviously, this is important in pregnancy when the fetal skeleton begins to calcify. And then we have a third value, TIC, which applies to transcranial ultrasound, where the probe is placed up against the skull, usually around the temporal bone, and so you have bone very closely adjacent to the probe face, so the machine models that particular situation in calculating the TIC. So at any one time, one or another of these 3 parameters will be displayed on the screen, and that will give you a pretty good idea of the likely maximum temperature rise. Now let's talk about cavitation. Cavitation refers to the behavior of gas bubbles in an oscillating pressure field. So it's obviously relevant to the interaction of ultrasound and gas bubbles. So the gas bubbles oscillate in size. They actually grow in size because additional gas is incorporated into them when they expand. So the bubbles grow in size and then they either stabilize, in which case we're talking about non-inertial or stable cavitation, or alternatively, the bubbles collapse rapidly, as shown in this diagram here. When the bubbles collapse, we refer to this as inertial cavitation or unstable cavitation. It's important because a very large amount of energy is released when the bubbles collapse in this way. This can cause significant chemical changes in the body and death of tissue and so on. So, cavitation is clearly a concern, and in particular the inertial cavitation. What affects the possibility of cavitation occurring? There are 3 parameters. First, you need to have small gas bubbles present, but of course that's the case in the human body. There are many situations where there are gas bubbles in the GI tract, in the lungs, and so on. The next important parameter is the maximum negative pressure value. And I'll show you on the next slide exactly what I mean by that. And then the third parameter is frequency. Luckily for us, the risk of cavitation, and in particular inertial cavitation, reduces as the frequency becomes higher. So the fact that we use such high frequencies in ultrasound helps to reduce the risk of cavitation. To give us an idea of whether cavitation can occur, and in particular harmful cavitation, the machine displays another index referred to as the mechanical index. This MI value is defined as shown here. It's a constant multiplied by the peak rarefaction pressure, which I've shown in the diagram, and then that's divided by the square root of the frequency. So the MI is basically a number It doesn't have a particular physical meaning. We can't interpret it as directly as the TI, but its value tells us whether cavitation, and in particular harmful cavitation, is likely to occur or not. Are there any other important biological effects that we would put under this heading of mechanical bioeffects? Well, there is one other really, and that's something referred to as radiation pressure or radiation force. When ultrasound strikes an object, such as some tissue, then if any of the energy is reflected or absorbed by that tissue, the ultrasound will exert a force on the tissue. So there is some force on every tissue that reflects or absorbs ultrasound. Normally, this is not considered to be potentially dangerous. There is one way in which it actually is visible or can be seen, and that's the phenomenon known as streaming. If you have a liquid with particles in it and you expose it to ultrasound, the radiation pressure on the particles within that liquid can cause them to flow away from the transducer. So you'll get a stream of fluid and particles within that fluid streaming away from the transducer. Is radiation pressure likely to be harmful? This is unknown. It is possible that there are circumstances where it is potentially harmful at clinical levels of exposure. So it is continuing to be investigated. So in summary, we have thermal bioeffects, which refers to heating, and the machine characterizes the likely amount of heating using the thermal index. Remember, no matter how long the exposure is, the temperature will rise by a certain amount, a certain number of degrees above body temperature, and then stabilize there. Then, under the heading of mechanical bioeffects, the important, potentially dangerous bioeffect is inertial cavitation, and this is characterized by the mechanical index, and the mechanical index tells us whether or not it is possible for inertial cavitation to occur. In the next talk, I will talk about how do we know what are safe levels of the thermal index and mechanical index, and how do we make sure that we're using ultrasound responsibly and safely.